Okay, good morning. From last week, we discussed chapter 1, which is reviewing the counting techniques to compute the probability in terms of, we interpret probability as the number of outcomes we are interested, divide the total number of possible outcomes. That's sort of some intuitive definition to compute probability. And in chapter 2, we are going to give the sort of modern formal definition for probability. That's called the axioms of probability. So for quite a long time, probability theory is not considered a rigorous math because it lacks a rigorous, solid definition, mathematical definition. So it looks like the foundation is quite weak. And about 100 or 120 years ago, Kolmogorov provided this 3-axiom probability that gives the first rigorous mathematical definition for probability. And after that, probability theory can be linked into the measure theory of mathematics, which is very long developed field. So anyway, these axioms serves as building blocks for defining and reasoning about probabilities in a rigorous and consistent manner. So these axioms allow us to compute and work and define define and work with probability rigorously, and allows us to use mathematical tools like set theory, calculus, linear algebra, and measure theory, many other advanced tools to analyze probabilities. So the goal for chapter 2 is to introduce this definition. In order to do so, we need to review some notions in probability theory. Basically, we review the operations of sets, and then we introduce definition for probability and use it to derive some probability properties that help us to compute the probability. And then in the last section, we are going to focus on a very special kind of sample space and how to compute the probability in that case, which links back to chapter 1. So it shows us the intuitive way to compute probability in chapter 1 is also valid when we are talking about the formal definition for probability. So anyway, start with a little introduction. So in chapter 1, we use this very naive definition to compute probabilities by counting things. However, obviously, this way of talking and using probability is quite limited. For example, it only deals with simple experiments when you have only finite possible outcomes, but there are way more random experiments whose number of total outcome is infinite, and it's maybe not even countable. For example, if you want to talk about the lifetime of your iPhone as a random variable, or the height of an adult in Hong Kong, so it has infinite numerical values for this possible value it can take. So we need to rigorously define probability. Here are some terminologies probability. So we usually talk about experiments or random experiments, which we introduced last time, whose outcome is a set of possible outcomes. And we talk about events, sample spaces, and then we rigorously introduce probability. So the definition for experiment is, we did last time, the basic object of probabilities and experiment. So it's an activity or procedure that produces distinct, well-defined possibilities. These are called outcomes. So the sample space is a set of all possible outcomes of an experiment. denoted by S usually. So here we use a set to include all possible outcomes, and the number set can be finite or infinite. Some examples, if you toss a coin, that's an experiment, and the possible outcomes are head and tails, and you use set S, the sample space, to be the set of these two objects. And also tossing two dice, you can define your sample space as the set of this ordered pair of numbers, ij. I is outcome you see in the first die, j is the outcome in the second die, so ij can run from 1 to 6. So there are 36 total possible outcomes in this sample space. And if you want to talk about the lifetime of a transistor, you can use sample space as this interval from 0 to infinity. So there are uncountable numbers in it. So that's sample space outcome experiment. And we define any subset E of the sample space is an event. So the event is another set. It's a subset of sample space. Okay. It's also a set. So usually you can see that we talk about sample spaces, events will work with the sets. So a sample space of a random experiment is a collection of all possible outcomes, while an event of a random experiment is a collection of some possible outcomes. Usually you collect those you are interested about. From the previous example, you toss a coin, you have a sample space as a set head-tail. If you are interested as the head occurs, you can use E equal the set of head to be a possible event. And for tossing two dice, we have a sample space as this set. And if you are interested in the event that the sum of two dice is 7, you can use the subset E to collect all these possible outcomes. For this one, you can list them out. There are 6 of them. And for the third example, the lifetime transistor, the sample space is interval from 0 to infinity. And one possible outcome is the set that this lifetime is in the interval 0 to 5. This is one possible event. So the number of events in the sample space, number of elements in the sample space and events can be finite or infinite. So this helps us to deal with more complicated random experiments. And also, if the random experiment produces an outcome in event E, we see that event E occurs. So if you toss two dice, and if you see a pair of 4, 3, for example, then you can say this event E occurs. These are some basic notions how we discuss probability. So think about this example. If we randomly roll 2 6-faced dice, which can be fair or unfair for each die, and let X denote number of first die, Y is the number of the second die. Just let's intuitively decide among the 3 events given, which is the most likely to occur. The first one is event E1 is this ordered pair XY, X equals 1, Y equals 2. E2 is X equals 2, Y equals 1. E3 is X plus Y equals 3. Okay, for this one, you can sort of have the feeling that because E3 contains the outcomes in E1 and E2, so as such, E3 includes both E1 and E2. So intuitively, this is more likely to occur. So you can see that probability is sort of linked to some kind of size or measure of the events. Okay, so before we introduce definition, the axiom probability, we review some operations on events. Basically, these are operations on sets. Probably you are familiar with. So anyway, we'll go over them. So first, the union of two events. Use A, copy B, a union to events B and A. It contains the outcomes in either A or B or both. So A union B is also a set, a collection of outcomes. It's also an event. For example, A is you choose a card, it's king. B is the event that you choose a card, it's still heart. A union B is your chosen card is either king or heart. So if you draw the Venn diagram, draw two circles, you can see A union B is both of them. So intersection represents the intersection of events A and B. It contains only the outcomes in both A and B. So it's also a subset, it's an event. Example, A is the select card king, B is the select card heart. So A intersect B now is the select card is king of heart. So A intersect B represents that both A and B occurs. If you draw the Venn diagram, one circle is A, the other is B. Their intersection is this red part. And also I'll mention that in the future I will just write AB next to each other to represent A intersect B, just for convenience. And the next operation is complement. We read this A superscript with a little c. This is a complement. It represents the complement of event A. It contains outcomes not in A. So it's also an event. This means even A does not occur. So in the Venn diagram, S is the sample space, A is a subset, so a complement is a part not in A. Another thing is the symmetric difference. We use A little triangle B. So usually it's A delta B. This represents the symmetric difference of event A and B. It contains outcomes in either A or B, but not in both A and B. Okay, so example, A is the select card's king, B is select card's heart. A delta B is the select card is either king or heart, but not king of heart. So in the Venn diagram, you can visualize this set. Two overlapping circles representing A and B respectively. A delta B is the part in A or B, but not in A intersect B. So this is also just a union B. Okay, so set minus, remove their intersection of them. A complement is also written as the sample space. Removed the A, the set minus A. Okay, that's the four basic operations. Let's also mention some more. Another relationship between events is called inclusion of events. For any two events A and B, if all the outcomes in E is also in F, then we say E is contained in F. We just read E, this notion, subset F. Or you change the direction, you write F, include E. Sometimes I think in other books you can also read a bar below this notion is also acceptable. So if you have this even E is included in F, this means the occurrence of F necessarily implies the occurrence of E implies the occurrence of F. So if you have E is included with F, this means if even E occurs, then even F also occurs. That's what we mean in terms of probability. Also, you can just use Venn diagram to sketch this relationship. E is a circle inside the circle F. Next remark is if E includes F, F includes E, then we have they are equal. Some additional concepts that's useful. The notion of disjoint is for two events. If they share no common outcomes, that is, their intersection is an empty set, then they are called disjoint. So basically, if you draw the events in a sample space, you see two circles do not intersect each other. Also, this notation, you draw a sort of a circle and cross it. This is empty set. And mutually exclusive. This is for multiple events. Of course, you can also consider two events to be mutually exclusive, meaning they are disjoint. So if you have events A1, A2, AK, they are pairwise disjoint. They are called mutually exclusive. Okay, so usually we just write, we don't write the words, we use math notations. For mutually exclusive, you can write the I intersect AJ is always empty set for any pairs I is not equal to J, and IJ runs from 1 to K. I'll just write this math notations for mutually exclusive. So some Venn diagram for mutually exclusive sets. So these are sort of not very obvious here, but have different colors. They do not overlap each other. And some other notions, exhaustive. So this means if the union of some events A1, A2, AK is the sample space, if the union of all these events is equals S, then they are called exhaustive. So as shown in this graph, these events may overlap with each other. But the next notion is called a partition. So this means if you have this events A1, A2 to AK, actually they can be infinite, countably many, but here let's just introduce this way. If they are both exclusive and exhaustive, or I should say mutually exclusive or exhaustive, we call them a partition. So partition of S, so we satisfy two constraints that first, they are exhaustive. So you take the union of all these events, you get to the sample space. Sometimes just write this union of AIs, I runs from 1 to K to represent this notation. Another thing is that they are mutually exclusive, they are pairwise disjoint. We just write in this notation. AI intersect J is empty set for I is not equal to J. It runs from 1 to K. So partition of the sample space or some event is a useful notion in probability theory. And next, let's review these fundamental laws regarding these basic operations. So these are our examples, just go over them quickly. The first one is called commutative law. So A intercept B the same as B intercept A union B equals B union A. The second one is associative law. So if you have intersection of 3 events, basically you can take intersection any 2 and then intersect the other one. Similarly also holds for the union. Okay, so the next one is distributive law. So if you have the combination of intersection unions, you can distribute them. So A intersects the union B and C is the same as A intersects B union A intersects C. So you distribute A intersect to the unions. And similarly, if you have A union, the intersection B and C, you can distribute A union to the intersection. And then take the first A unions, A union B and A union C, and then take the intersection of them. The last one is the De Morgan's law. This is also a useful one. It says if you take the complement of unions, you get intersection of the complements. And if you take the complement of intersections, you get unions of the complements. So you can see from the associative and distributive laws, it's very similar as what we do with the Euler multiplication or summation of numbers. It's like you can think of the same rule. And distributive is you have the combination of multiplication with the summation. You can distribute them. It's a same kind of law. And here, if you want, you can also to convince yourself about these laws using the Venn diagram. So maybe I just go over one. A intersect B union C, draw 3 overlapping. So I should draw the circles or something. Anyway, so A union B, A intercept B union C. B union C is just two. Together, these 2 rectangles together. A intersect them is this blue parts drawn here, and it can be viewed as A intersect B, which is this part. And union A intersect B this part, union A intersect C this part. So it's sort of obvious from the Venn diagram. And also for the De Morgan law, I will not go over them. It's very simple. You can use the Venn diagram to illustrate it. Maybe just write down the special case K equals 2. Just when you take the complement of unions, then you get intersection. If you take the complement of intersection, you get the union of the complements. Okay, the next small property we call the lemma. So this is actually a very simple but a very useful thing. Let me draw a triangle to that. it says this: if you have any two events A and B, then you can have A is equal to A intersect B union A intersect B complement. Okay, so in my shorthand notation, I usually write this is A equals AB union AB complement, right? This way, it's shorter. So what this lemma says that if you have any two events, then you can create a partition of one event using the other way, using the other event. So you basically partition this A in terms of the part in B and the part not in B. So it's what this lemma says. Okay, so you can either prove this lemma using the Venn diagram, draw two circles in the sample space. So you can see A is a part, A can be written as a part in B and part not in B. The union of these two disjoint events. So this disjoint form the partition of A. And also you can use the laws we just went over. You can start right-hand side. Notice that you can sort of see the union of A intersect something. You can factor out the A intersect, and you get B union B complement, which is a sample space. So you get A intersect sample space equals A. Okay, so that's our basic operations we want to review. Then now we are ready to introduce the axioms of probability, which is a definition for probability. So this goes back to the question, what is probability? So intuitively, we have the feeling that after this counting computation that a probability is a function that assign numbers to events. For example, you can say the probability of this event, the sum of two dice is 7, is 1/6. And this number reflects how likely this event occurs. The larger it is, the closer to 1, it's more likely to occur. So let's sort of have a try how we can define probability. For example, if we randomly roll this die and we want to find out how likely we'll get 5, this may not be a fire die. So how to describe this likelihood? So a naive but very intuitive idea is to say roll this die 1 million times, so maybe not 1 million, but many times, and count the number of times 5 is observed. Then we can compute this probability by the number of we see 5, divide the total number, like 1 million, to decide this likelihood to see a number 5 for this die. So this number we computed is called the relative frequency. This is very naturally regarded as a measure of how likely 5 is observed. And in the very beginning of probability theory, that's the formal definition for the probability of some event. So we define this through this limiting frequency, because you cannot just say, we just rolled it 1 million times for the die, and for if you toss a coin, let's also fix 1 million times and then compute the relative frequency and decide the probability. So it's not like that. You cannot fix the number time you roll the die of toss a coin, but we define it through a limiting way. We take the limits. So it goes like this. Suppose an experiment with the sample space S is repeatedly performed. And for each even E in the sample space, we can define this NE to be the number of times in the first N repetitions of the experiment that the even E occurs. So exactly as what we did earlier. So now we take the little n equals 1 million and count NE, the number of this number 5 is observed. And then define this PE, the probability even E, as this relative frequency NE over N, and we take the little n goes to infinity. So PE, probability even E, is defined as the limiting proportion of time that E occurs. So, well, this definition is very intuitive, and it's naturally describe how we can find the probability. But if it is used as a mathematical definition, it's less rigorous. Also, it will cause some contradictions or paradoxes. So let's mention several drawbacks in the previous definition. For example, it may raise the question, how do we know if the limit of this number always exists? That's not guaranteed. And even if the limit exists for all the sequences, how do we know that all these limits are the same? They may converge to different numbers. So for a mathematical probability model, we can certainly make an axiom to assume that we can assume this limit always exists and converge to the same constant value. But that will impose too many assumptions. So it will be too complicated to be a theorem, to be a definition. So the modern probability theory is built on the theorem called Kolmogorov theorem, axiom we are going to introduce later. This is a picture for this guy, Kolmogorov. He's sort of the father of the modern probability theory. Did a lot of significant contributions to the development of probability theory. So anyway, let's just introduce the 3 axioms. Okay, so it's proposed in 1933, so not even 100 years ago. Okay, so he defines the probability denoted by this capital letter P. You consider it as a function on the collection of events. So basically, we are going to view the probability as a function that assigns a number for each even E, but it obeys the 3 rules. So first rule is, or the first axiom is, for any event, this value PE you assign to the event is always between 0 and 1. The second axiom says, if you have the sample space, that's also an event, you always assume P, the sample space, this value of sample space is always 1. The third one is, for any sequence of mutually exclusive events, that means that, so this is an infinite sequence. It can be finite or infinite many. So they are mutually exclusive, meaning they are pairwise disjoint. So you always have the probability that union of these AIs is equal to the sum of PAI. Okay. So roughly speaking, probability is a function that assigns numbers or numerical values to events, and you should satisfy these 3 axioms. So not every function is a probability, but if you satisfy these 3 axioms, it's called a probability. So with these axioms, this Kolmogorov actually put the probability theory into a wider context of the measure theory in mathematical analysis. So we treat the property as a measure of uncertainty. And we provide a formal definition of property as a function that assigns numerical values to events. So the number you assign reflects the degree of uncertainty associated with each event. Okay. So once we have connected property theory with the measure theory, we are allowed to use more advanced tools from measure theory, from like integrations and many other martingales, many other advanced tools to study properties. Okay, so that's their definition for probability. And let's see this remark. And we just call PA the probability of the event A. And also it provides some explanation for each axiom. So the axiom 1 states that the probability that the outcome is in E is some number between 0 and 1. So the probability that an event occurs is between 0 and 1. And axiom 2 says PS, the sample space, equals 1. So this means that with probability 1, the outcome will be a point in the sample space. In other words, the probability that at least one outcome occurs is 1. Okay. And also axiom 2 also offers some normalization. So the sample space will have this probability equals 1, but you can imagine that you can assume that PS equals 10 and scale up everything accordingly. But it's convenient to work with values between 0 and 1 because it's related to the relative frequency of proportion, which is more natural for us. Axiom 3 says for any sequence of mutually exclusive events, the probability of at least one of these events occurring is the sum of their respective probabilities. And in some textbooks, axiom 3 is written as you work with a finite number of mutually excluded events. You sum f from 1 to some capital N. This N can be any number between 1 and 2. It's sort of equivalent. So we are going to show that axiom 3 we wrote here implies this statement. We'll see a proof later. Okay, so in the future, we are not limited to use the counting method to compute probability. We are going to apply the 3 axioms to help us derive the probabilities. So let's start with sort of an appetizer, a very small example to see how it goes. We roll a fair 6-face die. Randomly, we consider a number of the random outcomes. A is the set of the event 1, 3. B is the event 2, 4. Let's use Kolmogov's axioms of probability to compute the PA and PB. Okay, so we are given this die is fair. So the chance that we see any number on the die is the same. So first, the sample space in this experiment is the collection of the numbers 1, 2, 3, 4, 5, and 6. Okay, so let me, for convenience, let me note this probability of this event. You see a number 1, say, I just write P1, okay, just for convenience. I don't want to write the longer notation. Well, given this die is fair, this means the probability that we see any number P1, P2 equals P6, they are the same. Okay. And by the second axiom, we know that PS equals 1, the third axiom. Oh, sorry, the second axiom. And by the third axiom, because this S is, so this union 1, 2, 3, 4, 5, 6 is the sample space from the partition of S. They are mutually exclusive. So by axiom 3, we have this is P1 plus P2 plus up to P6. And these are all equal, so we get this for each P1, P2, they are the same, they are equal to 1 over 6. And then let's compute the probability of the events PA. Now we use the third axiom, 1 and 3 from a partition of A, so PA equals P1 plus P3 equals 2 over 6, 1/3. And similarly, PB is the same. It's P2 plus P4 equals still 1/3. Okay, so this is to help us to get familiar with using axiom to compute probability. Okay, for this example, we don't see the advantage of using the axiom, but later on, for more complicated questions, we will see that this offers more convenience than the counting method. So usually the counting does not work. Okay, so let's show some properties for probability. We will derive them directly from the axioms. So first property is the probability of empty set equals 0. Okay, we use the 3 axiom to derive this one. So basically, the third axiom provides more flexibility for computing the probabilities, because the first 1, 2 are sort of like tells us a range of the probability sample space equals 1. Okay, so we'll try to use the third axiom. So we construct a sequence of events. We'll set A1 equals sample space, A2 equals A3 equals all these other remaining events equals empty set. And we can see that this sequence of events are mutually exclusive. Because you take any pair of them to the intersection, it's always empty set. Then we can use axiom 3. The probably the union objects events equals their sample space equals PA1 plus PA2. That's the right application for the third axiom. So basically, PS equals PS plus the property empty set plus the property empty set. And this tells us this sum of property empty sets is always 0. And so this tells us that the property empty set has to be 0 because axiom 1 shows that this must be a value between 0 and 1. So Okay, the next property we also call the theorem is for any finite sequence of mutually exclusive events, A1, A2 to AN, the property of union of them equals the sum of the individual probabilities. So we use axiom 3 derivative. Axiom 3 is for any infinite sequence of mutually exclusive events. So we just complete this finite sequence to be infinite. So we define an plus 1 equals an plus 2 equals algebras equals empty set. So now we have an infinite sequence of mutually exclusive events. These are still mutually exclusive. Then the axiom 3 tells us the probability the union of these AIs I from 1 to infinity. But because the an plus 1 and the events after that are all empty sets, so this is the same as this finite union of the AIs. And the third axiom tells us this is the same as the sum of the PAI I from 1 to infinity. But because the previous theorem, we know that the probability of an plus 1 and an plus 2 of these probability empty set, they are zeros. So this infinite sum is actually a finite sum. Okay, let's see another property, the complement rule. So to write this is a complement rule. A is an event, then the probability of this A complement is 1 minus the probability A. So this is also a useful little result for us to compute the probabilities in the future. So to show this, we still try to use the third axiom. So we can see that the sample space equals A union A complement, and A complement are disjoint or mutually exclusive. So by the third axiom, we have PS equals PA plus PA complement, and we know that PS equals 1. Just second axiom. So we have PA complement equals 1 minus PA. The next property is called the monotone property. So this states in this way: if E is included in F, basically E is a subset of F, then PE is less than equal to PF. So this is the monotone tonicity. So basically, our function, probability the function is a monotone function. In terms of set language. Okay, let's show this property using the 3 axioms. And if we can show that property F equals property E plus some non-negative numbers, then this is done. So here we try to decompose the event F. So now we have two events. So little lemma we mentioned earlier is that you can always create a partition of one event using the other one. So let's write this F as a part in E union the part not in E. So we can write F as F intersect E union F intersect E complement. And because the relationship E is included in F, this means F intersect E is just a smaller event, it's E. So actually we can have F is the E union F intersect E complement. So these two events are disjoint. So by the third axiom, we have the probability of F is equal to PE plus the probability of F intersect E complement. And the first axiom tells us the probability of any event is non-negative. So this means the probability F is greater or equal to the probability of E. Okay, the next property is called the sum rule. Okay, this is also useful in computing probabilities. So this says if you have two events A and B, then the probability of the A union B is computed as PA plus PB minus PA intersect B. So it's generalized the third axiom. Third axiom says if A and B are disjoint, then PAB, A intersect B is empty set, so PAB 0 is gone. You get back to the third axiom. But now A and B can have intersections. So here we provide two kinds of proof. The first one is you can use this visualization by Venn diagram, and you sort of interpret the probability as some kind of area of the events, some kind of measure of them. So here, if you visualize using the Venn diagram, PA is this circle, PB is this circle, you can have intersections. So let's denote these three disjointed regions, this part in A, not in B as 1. The intersection is 2. And in B, the part in B but not in A is denoted by 3. You can think of a PA as P1 plus P2, and PB is P2 plus P3. And P8 intersect B is this P2. And we want to find the probability of the A union B is basically P1 plus P2 plus P3. And you can check how to make out this number using these relationships. So you use this PA plus PB. Use these two relationships, add them together. You get a P1 plus twice P2 plus P3. And in order to make it equal to this PA union B, you need to subtract one copy of P2, which is PA intersect B. Okay. Let's also give a formal proof using the axioms. Let's show that this left-hand side equals right-hand side. So we want to find the property A union B. The right-hand side will have a copy of PA. Let's first isolate that out. So let's rewrite this A union B as A union. So you can see this can be read as A union the other part, which is the part of B not in A. Okay, so you can write A union B as the union of these two disjoint sets. So by the third axiom, we know that this PA union B is PA union B a complement. You can write this as the sum of PA plus P B a complement. So the second step to show that this P probability of B intersect a complement equals this PB minus PAB. We are done. So in other words, we want to show PB equals the sum of these two probabilities. And then we need to use the little lemma we mentioned earlier one more time. So we can write B as these two disjoint events. You can create a partition of B using A. It's BA, it's the part in B, also in A, union the part in B, also in B, a complement. Okay. And this way, we also have this BA complement are disjoint. This means we can apply the third axiom. So PB equals PBA plus PBA complement. And rearrange the terms, we get PBA complement equals PB minus PB intersect A. And then we can insert this back into the first identity we have obtained to conclude this sum rule formula. PAB the same as PBA. Okay, so that's a sum rule formula. So tells us the property union of two events can be computed as a sum of the property of individual events minus the property of their intersection. Okay, now we have introduced the axioms and derived some properties for property T. We can turn to some concrete examples and do the computation. So hopefully for now you can use the mathematical language to answer what is property T. So you should always keep this in mind, at least for this semester. So property T is a function that assigns numerical values to each event. And this numerical value by the first axiom is always between 0 and 1. And you will assign 1 to the whole sample space. And also the third axiom is if you have a sequence of mutually exclusive events, the probability union of them equals the sum of the individual probabilities. Okay, now let's also take a moment to think about this one. Suppose a coin is tossed. The sample space you form is a set of head and tail. Then decides whether the following functions are probabilities, whether they are valid or not according to the three axioms. Okay, so for this one, it's actually very simple because only the choice B is the probability, because by the second, third axiom, the probability of sample space equals the probability head plus the probability tail should equals 1. So only the second one satisfies this one. Let's also sort of take a moment to do this computation. There is a 6-face die with numbers 1 to 6 on each face. We randomly roll this die. Suppose that the probability of getting a number bigger or equal to 3 equals 3/5. The probability of getting a number less than or equal to 3 equals 1/2. Then what is the probability of getting the number 3? So you can sort of try to compute this one. Okay, so you can use whatever method you want, but it's better to associate with your definition for probability, the set operations we are talking about. Okay, so maybe you can do it together, provide a sketch. So what is given is, let me just write it in a shorthand way. The probability of this number is bigger to 3 equals 3/5. So you can write this as the probability of bigger than 3 plus the probability equals 3, because bigger than 3, the union of these two disjoint events, this number is bigger than 3 or this number equals 3. So this is 3/5. And similarly, the probability you get a number less than 3 can be written similarly is probability less than 3 plus the probability this number equals 3 equals 1/2. And also we use the probability of sample space if this number is a 1, 2, or 6, you can also write this as is the union of this is bigger than 3 plus the property is less than 3 plus the property is equals 3. This equals 1. Okay. So you can write S as the union of these mutually exclusive events like this. And you have 3 equations. You want to find the probability this number equals 3. So you can see how to manipulate these equations to get this probability. So you can sort of like, you can use 1 plus 2 to get p bigger than 3 plus p less than 3 plus 2 copies of p equals 3 and subtract 3, equation 3. We get this probability equals 3 equals the sum of 1, 3 over 5 plus 1/2 minus 1 equals 1 over 10. Okay, so you can see these properties and axioms helps us to organize things more clearly using this set operations. Okay, let's work out another example. So in the following example, we have 2 events A and B. We got given probability B equals 5 over 8, and the probability A intersect B equals 1/2. Let's find out probability of B intersect A complement. Okay, so for this one, let's use the little lemma we talked about one more time. So if you have 2 events, you can create a partition of one event using the other one. So the lemma says we can write B as B, the part in A, B intersect A, union the part not in A. So union B A complement. And also BA and BA complement are disjoint. Okay, so it's a very useful little lemma. So then we can use the axiom 3 to get PB is a property BA union BA complement equals the probability of BA plus the probability of BA complement. We have this identity, and we are given this PB equals 5 over 8. We are also given the probability BA is the same as probability A intersect B equals 1/2. We are asking to solve the other one. So this is obvious. So the probability of B intersect A complement is 5 over 8 minus half equals 1/8. Okay, let's look at another concrete example in computing probabilities. So in this example, we are given J is taking 2 books along on her holiday vacation. With probability 1/2 or 0.5, she will like the first book. With probability 0.4, she will like the second book. And with probability 0.3, she will like both books. What is probability that she likes neither books? Okay, so now let's try to use this kind of language using the axioms, properties to compute the probabilities. So we need to first properly define the events. So let's denote this A1 as the event that she likes the first book. And similarly, A2 is the event she lacks her second book. Okay, these are two relevant events for this one. And what we are given, let's write down, we are given that with property half, she lacks the first book, so PA1 is 0.5. And with property 0.4, she lacks the second book, so we know PA2 equals 0.4. And we are also given that with property 0.3, she lacks both books. So we can express this event as operation of A1 and A2. So she lacks both books, meaning that both A1 and A2 occurs. So this is property of A1 intersect A2. This is a property she lacks both books. This equals 0.3. And now let's see what we are asked to compute. We are asked to compute the property she lacks neither books. So the event, let's first express this event using the A1, A2. She lacks neither. This means she doesn't lack the first one, so A1 complement, and also she doesn't lack the second one, that's A2 complement. So it's the intersection of these two events. It's easier to this one. So it's the intersection of the two complements. By the De Morgan's law, we can rewrite this as A1 union A2 complement. So in order to compute the property of this event, the property of this complement event, by the complement rule, we can first compute the probability of A1 union A2 and then apply the complement rule. Because computing the union of two events, we know there is a sum rule formula. So we can write this as PA1 plus PA2 minus P, their intersections, and all these numbers are given. So 0.4 plus 0.5 minus 0.3 equals 0.6. Then we can use the complement rule to compute the property we really want. So we're actually interested in computing the property of A1 union A2 complement. This is 1 minus the property of the union of A1 A2. So again, this is 1 minus 0.6 equals 0.4. Okay, so these examples show that if you're asked to compute probabilities now, you first start with defining the proper or the relevant events involved in the problem and figure out what's given and what is asked to be computed, and try to use the set operations or the event operation to relate the events you are interested about using the events you defined, and then use the properties or axioms or probabilities to do the computation. Okay, so lastly, let's mention a generalization of the sum rule formula. So here, because we have a formula to compute the probability of A union B as, maybe I'll just write down this PA plus PB minus PAB. But sometimes we also want to do the computation of probability of A union B union C. If there is a formula, it would be handy to apply the formula directly. So to get the formula, one way is use the Venn diagram to, like you just write this property of this event as this regions P1 plus P2, similar as before, the P plus P7, and then figure out what the P1, PA is, and PB is, using these things and try to make them work out to balance all these. Okay, so let's provide another way. Let's use this induction. So we can repeatedly use the sum rule formula. So first, maybe I just write down the few steps. You can use associative law. So you can think of this as A union this event B union C, and apply this sum rule formula once. Okay, and then this P, B union C, you can use the sum rule formula another time. So just plug in. Get the PB plus PC minus PB intersect C. Then A intersects or B union C, you can use the distributive law. This is AB union AC. You can see you can use the sum rule formula one more time. So use it 3 times. You can get this formula. So it's PA plus PB plus PC, the sum of individual events. Then subtract PBC, subtract PAB, subtract PAC. Okay. Let's skip the simplification. And then we sum one more term, which is the intersection of AB with AC. They simplify to ABC, the intersection of all 3 of them. So that's another formula you can use directly. So you can see the pattern. It's the sum of the individual events, then subtract the property of the pairwise intersections, then you add the intersection of the 3 events, and then actually, let me just mention that you can all further generalize it to have a formula for the property union of 4 events, 5 events, and it has a name. It's called the inclusion-exclusion principle. Okay, so let me just mention that, and maybe we do that next time. Okay, that's all for today. See you guys on Wednesdays.